So the way the review document is set up, at least for this review document, each chapter has its own section review, and we're restart numbering in the second chapter. So we got one chapter from 1 to whatever, and then the second chapter from 1 to whatever. So this is the first chapter, and we'll start off slow. So, and let me identify these as we go for the recording. Let's see, chapter 1. Chapter 1. And this is number 1. Maybe I'll write something up there, maybe I won't. Depends on the question. Which of the following is an example of a quantitative observation? What do we mean by quantitative? Oh, yeah. Yes, right. So let's see. A piece of metal is longer than a piece of wood. I don't think so. Solution 1 is darker than. Liquid in beaker A is blue. The temperature of the liquid is 60 degrees Celsius. So test taking technique, when you look at all the answers in a multiple choice scenario, and are there any oddballs at the end, like all of the above, none of the above, 2 of the above, that type of thing. And if those are not there, then you can just work your way down. When you get the right answer, stop. But if you got at least 2 of the above or quantitative, then you got to look at all of them. In this case, there's only 1, and that's 60 degrees is a quantitative observation. And about 2. Generally observed behavior that can be formulated into a statement, sometimes mathematical in nature. Did we cover that? Yeah, we covered that. So you have 2 choices. Is it a law or is it a theory? What's the difference between a law and a theory? Why? Laws are proven theories. Actually, a law just says what happens. Yeah. I've never seen a theory come before a law, but sometimes the theories come out of not thin air, but they're not based on law. They just appear, right, and go with them. But sometimes you have laws, and then a theory later takes those laws and makes sense out of them. Okay, so the well, in this case, natural law. At least that's the way the early 17th century on used to refer to things as natural laws. You'll even see natural law referred to in our forefathers' letters and writings when they referenced what did they base the Constitution and the Declaration of Independence on? It was natural law. Come on. Not going to work, is it? Let's try this. It doesn't like Adobe Acrobat. So I've got to do it manually. So let's work down to, let's see, is there a number there? Yeah, let's do this. Okay. So here we're dealing with prefixes. We want to order these prefixes from smallest to largest. So what I would do if I was faced with a question like this, I would scan them and see are the same ones represented in each selection, A, B, C, D, E. Let's see, nano is in everyone, milli is in everyone, centi is in everyone, kilo's in everyone. So which is the smallest out of that group? So we can just look at the first one and say, which is the smallest one out of here? nano, right? 10 to the minus 9. So we know that the one that starts with nano, actually that solves the problem for us. None of the rest of them had nano to start with. Test taking technique, efficient. Answer those questions and move on. But you can check it to see. How about milli? 10 to the minus third. Centi, 10 to the minus 2. And kilo, 10 to the third times, 1,000 times. So that one was A. All right, that's working now. Sort of. It's going to chop 7 off, so I might as well scroll with it. There we go. Number 6. I shouldn't dawdle today because we want to get to the lab. 8.1 kilograms. Contains how many grams? This is a unit conversion problem. We're going from kilograms to grams. So if you know what the prefixes mean, this one you can go pretty quick to grams. Right? Kilo means 1,000 times, right? So it's like saying 8.1 times 10 to the third, right? What's this part? Grams. Okay. Or if you wanted to use dimensional analysis, you could say it like this. Right? Kilograms on top, kilograms on the bottom, grams on top, 10 to the third. So the kilograms cancel, leave you with grams, 8.1 times 10 to the third. Works either way. That's 7. Convert 0.3980 meters to millimeters. For this one, I think it'd be easier to use the dimensional analysis. You want to go to millimeters, so it means millimeters have to be on top and meters has to be on bottom to cancel. So how many millimeters in a meter? 1,000. So that times 1,000, let's see, it's a mixture. So see, if it were scientific notation, it'd be 3.980 times 10 squared. Is that one of our choices? No. So we have to put it in standard notation. That's 100 times. So we move 1, 2, 398.0 millimeters. Holler if I lose anybody, okay? Or better yet, if you don't need this, say so and we'll skip on to something else more difficult. What's the measure of resistance an object has to change in its state of motion? We didn't put it in those terms exactly. This is actually a statement of Newton's first law of motion. Mass. Yeah, mass. Mass is a measure of how much substance there is. And if you have a certain mass and it sits still, it's going to take some push to get it going. Or if it's already moving, it's going to take some push to slow it down or speed it up. That's essentially Newton's first law. Weight, though, is itself a measure of force. So that would be the force applied to the mass, or it would be the force actually. I'm going off track there. Weight is how much force the mass applies in a gravitational field. So standing on the earth, I'm applying about 200 pounds of force to the floor. And it's pushing back with the same amount, right? If it wasn't, I'd go through the floor, correct? And volume and length are just put in there to confuse, along with none of these. So really, it's a decision between mass or weight. And mass is an expression of inertia. So that was A1. All right. Oops. Not far enough, and this magic wand doesn't have a scroll key on it. 11. As part of the calibration of a new laboratory instrument, 1 gram mass is weighed with the following results. So we rated it 3 times on the instrument, and it came out with 1.201, 202, and 200, plus or minus 0.001. Those values were given by the instrument for 1 gram mass. So what does that tell you about the instrument? First of all, it's not accurate. Okay. But is it precise? Are they grouped together? Well, we're claiming a variability of plus or minus 0.001, and yeah, they're really close. So this is not accurate, but precise, which is what? C. Okay, everybody see how that came about? Okay, I wouldn't want to have to use that instrument. Although I have mentioned this before, but we can divide error, particularly laboratory error, into 2 types, either random or systematic. This is systematic error. It occurs the same way, similar over and over and over again. Systematic error can be dealt with. No, I'm sorry. No, this is not systematic error. It's apparently random, but it's not very broadly based. Systematic error is the same kind of error that happens every time. Like when you measure a length and it's always 1/10 of a meter high every time. That can be accounted for. But if it jumps around, you don't know what it's going to be in that 3rd digit. That's random error. And we have to deal with that statistically, which we're not going to put a lot of weight and emphasis on that in this course, but you should be mindful of it. How about this? Let's see. Chopped off the bottom one, didn't it? Let's go down like that. There we go. Okay, 12. Which of the following figures represents a result having high precision? Okay, so it's kind of a take on the previous theme. High precision would be close grouping, right? So I'd say Roman numeral 1, no cigar. Roman numeral 2, yeah, those are precise. Roman numeral 3, yeah, those are precise. So 2 and 3 look like they have tight grouping of impacts on the target. And that would be E. Figure 2 and figure 3 are representations of precise measurements. That's E, right? Oops. Next one is 13. Here we go. Which of the following statements concerning these figures is correct? Oh, we're talking about the correct. Okay. So let's look at this and then we'll scroll back up. Figure 1 represents systematic error. Oh, I didn't have one in there. Systematic error. Figure 2 represents random error. So let's go back since we know the context of the answers. Let's go back up and say, all right, which is random error? I would say number 1. Right? There's no rhyme or reason to it. So 1 is random. And based upon my assumptions here, the previous question, that was systematic error. Right? It was pretty close to the same off each time. But this grouping is wrong by the same amount, similar amount each time. So 2 would be systematic error. We could claim 3, but let's see. Figure 1 is random error, yes. Figure 2 is systematic error. That's right. And figure 3 is virtually no error. And at 16, the amount of uncertainty in the measured quantity is determined by what? What determines the uncertainty of a measurement? Well, 2 main factors. One is the instrumentation. No instrument's perfect. And the other is the operator, the skill of the observer. Those 2 together account for all of the error that I can think of. So A would be the answer to that. Think of any others? Yeah.
So question 13, the one that we just went over a second.
Yeah.
Right, the bottom, it says figure 3 represents no error.
Oh, you caught that. Figure 3, yeah, it's a bad question. Because there is some error there, right? A little bit. So I better not put that type of an answer in a question. Otherwise, I have to accept B or E, wouldn't it? Oh, and I didn't say anything about this at the beginning. A rule that I've always had is you're not going to suffer from my mistakes. Like if I make a mistake on an exam and I put a bad question in there, show it to me and say, you argue your point. The answer could be this or this, then you get credit for it. That's an example. Okay. So we did 16, 17. I better scroll that a little bit. 17. A scientist obtains this number. Let's see, 0.045006700. Okay. On a calculator, if this number actually has 4 significant figures, how would you write it? How many, which of these are significant as it is? Right. These guys right here. Right. These zeros are captive. These zeros don't count. These zeros count because there's a decimal there. Okay, so we start counting from here. And if we need 4, we go 1, 2, 3, 4. Right? This one is greater than 5, so we would write 0.04501. Okay. Let's see, 17. Roll that one. And then we get this one too. How about this one in scientific notation? 20. 0.0810. Scientific notation. What do we have to do with scientific notation? We've got to store up movements of the decimal in powers of 10, plus the coefficient that results has to be between 1 and 10. So we could move it over here, 1, 2, right there. And that would make the coefficient that. And then the power of 10, since we moved to the right, minus 2. Because we were storing up small number. Tenths, hundredths. Tenths, hundredths. Okay. And that's D. How about 21? Put this one in common notation. 6.49 times 10 to the minus 3. Okay, so we take this for 9. Since it's minus, we're going to be moving the decimal this way. We got to make a small number, right? That means small. So I just put a few zeros out here to accommodate the movement. So we go 1, 2, 3. There we go. 0.00649. Okay. I don't even have to put this one up, I think. You're going to be able to move the decimal which direction. It's a positive power of 10, so it's going to be a big number. All right, so we move it to the right. And we're going to move it how many places? 4 places, so it should be 2, 3, 7. 1, 2, 3, 4. 23700. And expressing it that way means that there are only 3 significant figures here. And in the original number, only 3 significant figures. I see a problem if we had a number like this, 2.370 times 10 to the 4th. And you would move it 23700, and you're kind of stuck because you can't put a decimal in here to make that 0 significant, can you? So that looks like it's a glitch in the system. This says it's only got 3, but we know it has 4. But when we convert it to standard notation, you know, what are you going to do? Put a caption. Say, this number really has 4 significant figures. So I'm not going to give you any like that anyway. We'll leave that for the experts. 23. We generally report measurements by recording all of the certain digits plus how many uncertains? Just 1. Right. All the numbers from left to right are certain until you get to the last one. The last one is your guess, your estimate. Okay. You're asked to determine the perimeter. The perimeter of a cover on your textbook. You measure the length as 39.36. Sometimes drawing a picture helps. 39.36 centimeters long and 24.83 centimeters wide. So what's the how many significant figures should you report for this? Which one of the rules are we going to use? Has to be add subtract, right? If it's perimeter, we have to add them together. So we would put another one here for the other side, and then we put these two, 24.83, 4.83, and add them together. So if you're going to just say how many significant figures, it's possible to estimate. So this is about 40, that'd be 80 plus 25, 20, 50, 18, 25, 130. So you're going to have a position here, 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 and here, because you can keep everything up to that point. So I say you have 5 significant figures in the answer. And if you don't trust yourself, go ahead and add it together and you'll find out. But I used estimation because I knew that all we wanted was to know, is there another digit placed out here by adding these together? And yeah, there is. There's another digit there. I don't have to know the answer. This answer to answer that question. Okay. Estimation is a good habit to get into because it helps you answer the final question. Does the answer make sense? If you can do estimations. 25. Consider the numbers 2368 and 412. The sum of these numbers has 2368 and 412. Okay. The sum has how many significant figures? Well, let's see. That's going to 2 decimals. It go all the way to here. You have 1 there, 1 there, and there. It doesn't go bigger than that, so you should have 4. And then the product should have 3. So it's 4 and 3. That's D. Okay. Using the 2 different rules, add, subtract versus multiply, divide. Am I boring you? No. You're yawning. Don't get me started. During the semester, I'm good to get 5.5 hours of sleep. You may even get less. Yeah. Especially if you're working, going to school, got a family. Yeah. But I'm older than you. I need more sleep. Using the rules of significant figures, calculate the following. 4.0021 0.10 no 1, excuse me, 179. 179. Okay, so we're going to subtract that. 3, so that's 2, 1 from 9 is 8 and 3. So how many of these can we keep? We can go to that decimal place right there. So the answer is going to be 3.823. We have to throw that one away because if we put a 0 there, it's significant. We can't put a 0 there. That's A. All right. How about 32? Here we have a combination. 3.478 times 1.164 divided by 2. Let's see, this is grams. This is milliliters minus 0.169 grams per milliliter. How do we approach this problem? Well, fortunately, we have parentheses. Right. Parentheses first. So we would multiply those 2 together. I'm going to use a calculator for this. 3.478 and 1.164 times. So it's parentheses, no exponents, multiply, divide. So we do this one, then divide. And since they're the same rules, we could do it all at once. So I'm going to divide by 2. Okay, so I get, for this calculation right here, I get 2.024196. So for this part of the calculation, I'm limited to 3 significant figures. And the reason I have to round it now is because we've got a different rule operating for that next one. Right? The significant figure rules don't transfer across one another. So this one has to be rounded to 3 significant figures. Then we subtract 0.169. Let's see, that's 6 from 11 is 5. 1 from 9 is 8. And 1. Now, this is not lined up very well. Let me move that over. That. So we have to round to that position, 1.85 grams per milliliter. Okay, and that's C. Okay. Okay, 35. Express the volume in liters. 781.2 cubic centimeters, and we want liters. Okay, how would you approach this one? Well, it's dimensional analysis. And if you want to be complete, cubic centimeters to milliliters is 1:1. Exactly the same. But then we want to convert milliliters to liters. So this is 10 to the third, 1,000 milliliters per liter. And there you go. So we can do this in our heads, right? One there, one there, one there, one there. This would be 781.2 times 10 to the minus 3, right? That's in the denominator. So when it comes up here, change the sign, right? So then we can move the decimal. Let's see, this is going to be standard notation. Okay, so move it 3 places to the left. So we're going to be over here, 7812. And these have no bearing on the significant figures. They're exact numbers. Conversion factors are always exact. So this one determines 4 significant figures, 4 significant figures, and this is liters. That's D. Okay. Let's see here. 37. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. That's 1 atmosphere. Actually, it's 14.69, but we'll stick with the problem. What's the pressure when expressed in grams per cubic meter? This is a chained conversion. You need several conversion factors to get to the end. So we're starting from 14.7 pounds per square inch. When you have a conversion, when the answer is going to be in grams per square meter, when the conversion is going to involve 2 different units that are being converted, do one at a time. So I'm going to convert pounds first into grams. Pounds here and grams there. Do we have a conversion factor for that? No. Kilograms. So the conversion factor is 2.205 pounds per kilogram. It gets rid of pounds, but now we've got to convert kilograms to grams. 1,000 grams in a kilogram, right? Okay. So that and that. Okay. I'm gonna have to snake around. Now we can work on square inches. So we want to convert square inches to square meters. So we know that inches has to be on top because it's in the denominator here. Inches for this conversion factor has to be on top. So what do we know? Well, we're given centimeters. 2.54 centimeters is an inch. So what's wrong with that picture? That's squared. That's not squared. So here's the easy fix for that. Square them both. So that will square this, square that, cancel this, and square that too. So now we got square centimeters. It's in the denominator, so I need centimeters and meters. So there are 100 centimeters in a meter, and we're going to square that one too. So that's square centimeters per square meter. Right. We've worked our way down through all of these units. The rest of it is number crunching. All right, so this is starting with 14.7. We're going to divide it by 2.205. Then we're going to multiply it by 1,000. Then we're going to divide it by 2.54 squared. 2.54, where's my square button? There it is, squared. Divide that into it. And then we're going to multiply it by 10 squared squared. So what's that? 10 to the fourth, right? 10,000. So I get, oh, it's in scientific notation. Oh, how did I lose that? I thought I had it set up for scientific. Let me change it there. Scientific display. Here we go. Scientific. And I want maybe. Yeah. There we go. All right, so you can set your calculator up to spit the answer out in scientific notation. You just have to learn how to do it over your calculator. So I've got 1.0333, sorry, ad infinitum, times 10 to the 7th. These are all conversion factors, right? So they're exact numbers. We have 3 significant figures. So we're going to stop right there. 1.03 times 10 to the 7th. And this is I crossed out grams. It's grams per square meter, which is B. Okay. Let's see this one. This is another chain conversion. Do I have time to do it? We got to finish by 30 minutes. I better skip this one. You're going to have to do the similar process to the last one, a series of conversions. And since you've got none of these units are cubed, and you want to end up with a cube down here, remember that trick. You set up the linear conversion, and then you cube the whole thing. Okay, and check yourself to see if cubing it will give you the right answer. Because I haven't even gotten chapter 2 yet. Let's see, during the physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? Okay, I'll set this up, but we won't work it. We'll just set it up and then there'll be the answer, just to save time. So where's your starting point? You want to end up with miles per hour, but your starting point is given here. The speed of light is 3 times 10 to the 8th meters per second. But it's not that value, right? It's 93%. So there's the fractional equivalent to 93%, 0.93. So if you multiply that times this, that gives you your starting speed. Okay. Then you convert your units. Let's see. It's supposed to be seconds, wasn't it? Yeah, seconds. Okay, so we'll do one conversion at a time. We're going to do meters first. And we want to end up with miles. So what are the conversion factors? Again, kilometers per mile. right, so we want to get rid of meters. But we got to have kilometers. Because that's our conversion factor. So we have 10 to the third meters per kilometer. Okay, there we go. Now we can convert kilometers to miles. Let's see, what is it? 0.6214 miles. There we go. So that gets rid of kilometers. Now we're miles per what? Miles per hour. Okay, so I'm gonna snake it down here. Seconds, but there. Does anybody know how many seconds are in an hour? Okay, so we have to do a chain. We know that there's 60 seconds in a minute, right? That gets rid of seconds there. And then minutes in an hour per hour. Minutes. 60 minutes in an hour. Oops, per hour. There we go. So that's the thinking part. The rest is number crunching. So how many seconds are there in an hour? 3,600, right? So the next time you counter this, you can put that all together in one conversion factor. 3,600 seconds in an hour, if you need it. And the answer should come out 1 times 10 to the 7th miles per hour. Actually, that's not right. Because we started off with 3 significant figures. Oh, excuse me, I chopped off the bottom answer. No, 6.2 times 10 to the 8. That's not right either. Because that's only 2 significant figures. We just threw away a decimal point. So if we calculated that out, then you would keep 3 significant figures. But I will say this. If you encounter a question like this on a test, and you have these selections, choose the best answer. It may not be the exact answer you got, but if it's the best answer, it's probably the one that'll get you credit for the question. Now, if you think there's something wrong with the answers, you show me your work, and we can agree that you did it right, then I'll give you credit. Okay. It's kind of like going before your committee and defending your PhD thesis, right? You can support your arguments, then they got to give you your degree. Well, they don't have to, but make a good argument anyway. That means you know your stuff. That's what they're looking for. As much attitude as accuracy. 49. In 1928, 29.3 grams of a new element was isolated from 660 kilograms of the ore molybdenite. The percent by mass of this element in the ore was. Okay, this is a simple calculation. There's a lot of blue smoke in there, right? Who cares 1928 when it happened? As far as the calculation goes, you don't need that. What you need is 660 kilograms of the ore. 660 kilograms is the total mass. Okay. And 29.3 grams of the element were isolated from that. So the mass of the element is 29.3 grams. We want to know the percent by mass. Okay. So can we do the calculation with what we got there? No, units don't match. That's the kicker. You either got to convert this to kilograms or convert that to grams. I say convert that to grams, it's easier. Right? Because kilo means 10 to the third. So it's like that times 10 to the third. And that's in the denominator. 10 to the 5th grams is the total. And this is how much the element is that came out of it times 100. Okay. And if we do our math right, that should be 0.0044%. And that's right, I think. I made a mistake. I was claiming an extra significant figure is not there because that's not significant. So that's correct, and this is correct. Okay. Convert Kelvin to either Fahrenheit or Celsius. So how would you approach this one? You're starting with 409. Okay. You got to convert to Celsius before you can go to Fahrenheit anyhow. So why not convert to Celsius and see if it's one of those answers? So what do you do to convert this to Celsius? What's the magic number? 273. Okay. Subtract 273 from that. And what do you get? Well, let's see. 6, 3, 1 degrees. See. 136. There it is. Okay. So we don't even have to go to Fahrenheit. Okay. We found our answer. If we were, well, let's see. We'll do 51. Because 51 is a conversion to Fahrenheit. We've got 391 degrees Celsius, and we want to convert to Fahrenheit. So what's the formula? Right. It's in your useful information. But I've got mine memorized. 9/5 C plus 32. So that's set up the way we need it because the answer is in Fahrenheit. So what we need is 9/5 or 1.8 times 391 plus 32. And that should be equal to 736 degrees Fahrenheit. Okay. Let's see. I'm not going to do too well if we can't even get to chapter 2. In 1984, and what do you say? Who cares? Some drums of uranium hexafluoride were lost in the English Channel, which is known for its cold water, about 17 degrees. Okay, so the water is 17 degrees C. The melting point of uranium hexafluoride is 148 degrees Fahrenheit. 148 Fahrenheit. In what physical state is uranium hexafluoride in these drums? I'd be willing to bet it's still solid. Right. So if you're pressed for time, I'd say solid go. Or you can do the calculation if you have time. But it's going to come out at less than 148 degrees Fahrenheit. All right, what's let's see. 20 degrees Celsius is 68 degrees Fahrenheit. Right, that's my starting point. So if I drive by a bank and I see the temperature being flashed on their sign, you know, they'll flash Celsius and then they'll flash Fahrenheit and then they'll do something else and then they'll go back, cycle. I can't stop and wait for mine to come around. So if it comes up 25 degrees Celsius, I know to add 9 degrees to this one because the ratio is 9/5. So for every 5 of these, there are 9 of those. So if it goes 25 here, that means it's 77 here. Or you can go the other direction. If it's 15 Celsius, then I know it's 59. Right? And if it comes up here with a number like that, for every 9 of these, I know I had 5 of these. So you can estimate. I was trying to save time, but I didn't. I had to add my comments. 56. This is an interesting one. a mono layer containing 3.23 times 10 to the minus 6 grams of oleic acid. So mass is 3.23 times 10 to the minus 6 grams of oleic acid. What's oleic acid? It's a fatty acid. And when you take a true fat, has anybody had the anatomy and physiology? Okay, they talk about true fats, don't they? They're triglycerides. You take 3 fatty acids and stick them on the side of a glycerol molecule, and you got a true fat. Well, one of those possibilities is oleic acid. Well, if we take pure oleic acid and we drop that much of it on water, it's going to repel the water, but it's going to spread out into a single layer of molecules. And the way it's going to spread out is fatty acids have 2 ends to them. One is hydrophobic and one's hydrophilic. The hydrophilic end, the acid end, associates with the water. And then the tail, the long tail, sticks up, it's hydrophobic. So it sticks up like that. So that means if it spreads out in a layer, then they're all side by side with the acid end toward the water and like that. So you can tell how long is the molecule if you do some calculations, and that's what we're going to do here. So we form this mass, spreads out to an area of 20.0 cubic centimeters. The density of oleic acid is 0.95, 0.895, excuse me, grams per milliliter. What's the thickness of the monolayer? That is the length of the molecule. Okay, so this is a multi-step problem. If you're going to find out what's the length of the molecules, think of it as terms of a cylinder that's really thin but big. So if we draw the cylinder like this, right, then the molecules are going to be up and down like this. So this is the height of the cylinder, is the length of the molecule, times the area equals the volume of the cylinder. Right? So we're getting at that. We know this one already. We may have to convert the units, but we know that the area is that. Right? So how do we get the volume? Because we have to have the volume before we can calculate the height of the molecule. So you get the volume from the density, because we know the mass, right? And density is mass per unit volume, right? So we know this one, we know that one, we can get this one. All right, so since this is cubic centimeters, we want this one to be cubic centimeters too, right? And 1 milliliter is a cubic centimeter, so we can substitute the value. All right, so if we put this one in here, we solve for volume, what would that be? Volume equals mass divided by density. I'll just do a little algebra. So if we put the mass here, 3.23 times 10 to the minus 6 grams divided by the density, 0.895 grams per cubic centimeter. Remember, when you have a fraction in the denominator of the denominator is the numerator. And so this cubic centimeters becomes the numerator. And that numerator cancels that denominator. So if we divide that one, 3.23 exponent minus 6. Okay, here we go. And divide by 0.895. Then I get the volume is equal to 3.6. And since all of our calculations are multiply, divide, I can keep all of my decimals until the end. So I'm going to do that. Does anybody remember why? to minimize rounding error. Every time you do a calculation, if you round, what if you round up every time, right? Your error gets bigger and bigger. So I keep all my decimals. As long as every calculation is multiply, divide, one of those, then I do all the calculations in a sequence. And then go back into the calculations and say which one had the least number, then I round. And that eliminates error. So there's your volume. So this volume fits in here. Right? This one right here goes right there. So this would be that value divided by this value, wouldn't it? I don't hear any objections. So this value divided by 20 is, so the height of the molecule should be, and I'm going to round. So what am I limited to 3 here, 3 there. That doesn't count because it's a conversion factor. So 3 significant figures. 1.80 times 10 to the minus 7 centimeters. There it is, D. Okay. It was a multi-step problem. So what you have to do is ask yourself, you see what the question says, what's the thickness of the monolayer, but that's not the whole question. When you convert the question into what does it mean in terms of calculations, it means what's the height of that cylinder? Then you've got something to work with because you know that height times area equals volume. And then you can work backwards through the information that was given. Gets easier with practice. 57. We might have to bleed over a little bit in the lab, but I don't see any other way around it. The labs are not due till next week anyway. So we've got time. The density of gasoline is 0.7025 grams per milliliter at 20 degrees. What does that mean? Well, we know gasoline, first of all, it's not going to mix with water. Not if you pour it smoothly on top. Right? If you pour it into the ocean, of course, wave action mix it in. But it's it's less dense than water. Right? Density of water is about 1 gram per milliliter. It's going to float. Right? So if you dump gasoline on the lake, you're going to see it spread out on the surface. And you're going to see pretty colors too. When gasoline is added to water, oh, I'll give you the answer already. It'll float because what you need is to compare densities. Density of water is 1, density of gasoline is less than 1, it floats. Uh, 58. A piece of zinc with a mass of 12.14 grams. So mass is 12.14 grams. Is submerged in 46.3 centimeters of water in a graduated cylinder. So the initial volume, it says it starts at 46.3 milliliters. The water level increases to 48.0 cubic centimeters. The final volume is equal to 48.0. Okay, they're saying cubic centimeters. 6 of one, half a dozen of the other. What's the density of silver? Well, the question is density, so you've got to know this. Density equals mass divided by volume. We know the mass, right? Got that. What's the volume? Right? We got the volume by difference, didn't we? When you put the zinc in the cylinder, started off at this volume and it was at that volume. So the volume of the zinc is the difference between the two, correct? 46.3 here, 1.7 cubic centimeters. So we've got density equals 12.14 grams and 1.7 two significant figures, cubic centimeters. So the best answer is 7.1. Is that reasonable? Well, this is less than 2, almost 2, but 2 times 7 is 14. So yeah, we're in the ballpark. Use estimation to check yourself. Now that estimation would say, maybe it's this one and maybe it's that one. So how do you tell the difference? Two significant figures. That'll break the tie. All right. The boiling of water is what? Boiling of water. Sometimes you have to look at the answers to find out what the question is. The boiling water is a physical change or a chemical change, all right? Chemical and physical. Okay, boiling water. What's required to distinguish between the physical and the chemical change? The identity of the substance. When you boil water, does the identity of water change? No, it's a physical change. So let's see if one fits that. Physical change because the water merely disappears. No, you could disappear stuff with a chemical change too. It could react and all the reactants turn into gas. So technically it disappeared. In this case, the physical change because the gaseous water is chemically the same as the liquid. That's the key. The identity stays the same. Alrighty. Lots of repetition. Oh, this is a good one. The reason I've selected this one, and it goes on down below, but I want to point out some things about these particular figures. Notice the colors. There are whites and grays, okay, and their shapes. We got circles and squares. And some of them we have big circles and little circles. Okay, so take note of those differences. Get the cursor out of the way. Okay. So if we look at the question, which best represents a homogeneous mixture of an element and a compound, that gives you a clue as to what you're looking for here. How do we know compounds in this format? We have two of those shapes together, two or more shapes together. That would be a compound. Individual shapes mean elements. Okay. So if we look at 70 and say which represents a homogeneous mixture of an element and a compound, we look for mixture first. Which ones would be a mixture? Well, we've got differences here, right? Oh, there's a diamond too. So there are mixtures of different things in here, but these are representing atoms. This one is pure. There's only one form in there. That's not a mixture. This is a mixture, but it's a mixture of elements. Right? So we need an element and a compound. Okay, so here we have compound, but it's not a mixture. And that's not a mix. That's a mixture, but it's not. It's all element, all element, all element. So these two have compounds in them. And this represents an element, and that represents a compound. Now the other question is it homogeneous? Well, actually, we could answer it before that because these are compounds, but there are no elements in there. So this is the only one that fits, whether it's homogeneous or not. It's an element and a compound. And none of the others have that. But if we look at the conditions, homogeneous, yeah, it's homogeneous. If you look at the way these are distributed. So the answer to this one, this question is E. Let's see, 71. Which best represents a gaseous compound? Okay. So how do we know a gas? The particles in a gas are far apart, right? And they fill the container. So, is that a gas? More than likely. But, oh, actually not but, it is. This is compound. This is a gas, but it's a mixture of elements. This is a gas that is a compound. These guys are not gases. Yeah, I guess you could, these are not far enough apart. Besides, it's a mixture. It's not, let's see, a gaseous compound. This is not a gaseous compound because it's got compounded elements. So this has got a compound and it's configured like gas. The particles are separated far apart. Okay. So that's C. Let's see if it's right. C, yes. Okay. Which best represents a solid element? Okay. It needs to be an element and then it needs to be a solid. So which one's an element? All right. That's a mixture. That's a mixture. That's a compound. That's a compound. This is the only one that's a pure element and it's regularly arranged. That's a solid. So B is the answer for this one. Okay. The reason I wanted to stop on this one because sometimes those theoretical representations are kind of confusing. Oh, and the last one, which best represents a heterogeneous mixture of two elements? All right, so we need two elements, no compounds. All right, so that one's out. That was definitely out. This one's out. Okay. Here we have two elements, light and dark. Here we have two elements, and maybe three. But it has to be heterogeneous. Remember what I said about gases? Gases always form homogeneous mixtures, every time. So this one cannot be it. That's a gas. It has to be this one. That is definitely heterogeneous. Okay. All right. Which of these has a different value on the moon than on the Earth? Mass? No, mass is mass. All over the universe. Same mass. Weight? Yeah, weight changes. When you put a mass in a gravitational field, that determines the force that's applied by the mass against the surface of the object. Time's the same all over, and moles are the same all over. Which separation technique is based on differences in the volatility of the substances to be separated? This is a physical, we're basing the separation on physical properties. So we need to address volatility of the substance. So what does that mean? Usually we're talking about liquids. So two liquids mixed together, they're different volatilities. So they can be separated if you start heating them up. And the more volatile one comes off first, based on its boiling point, usually. So does filtration do it? No, that's particle size or phase. Distillation, that's a good, yeah, distillation will do it. Right. Ask any moonshiner. If they know how to get ethanol out of their mash. What's the first thing that comes off when a moonshiner heats up the mash? It's bad. Methanol, wood alcohol. That's the stuff that make you go blind when you drink it. So the first thing that comes off, they catch it in the jar and toss it. And they know by experience when the ethanol starts to come off, they catch that. That's the good stuff. Solvent extraction, no. Paper chromatography. Paper chromatography is based upon affinity of a substance to a surface, the paper. So it attaches to the paper, and as the mobile phase moves up through the paper, it exchanges between the paper and the mobile phase. So when it's in the mobile phase, it moves, and then it attaches to the paper. So those things that are more strongly attracted to the paper move slowly because they're not in the mobile phase very much. And the ones that like the mobile phase more than the paper, they move faster, and you get a separation. Okay, now we're in chapter 2. And I'm out of time. Technically speaking. I think we need to finish chapter 2 and then go on to the last. Okay, so let me change this. This means we're in chapter 2 now. Uh-oh. Says my battery's down. It's plugged in. No, it's not. Little scamp. Still recording. That's good. Get this back there. Hitch everything. There we go. The first people to attempt to explain why chemical changes occur were who made the first attempt that we know of? The Greeks. They tried to explain changes in substances with their atomic theory. It had its flaws, at least they were trying. How about 2? The first chemist to perform truly quantitative experiments was. Anybody? Well, the answer's up there. Robert Boyle. He did quantitative experimentation. How about 3? The scientist who discovered the law of conservation of mass is also called the father of modern chemistry. Okay. He was the one that lost his head in the French Revolution. Lavoisier. You know, his mistake, besides being wealthy, his mistake was he bought the contract from the king to collect taxes. And tax collectors were hated just as much back then as they are now. So you bought a contract from the king and you collect the taxes, and the king said, I want this much. So you give him that much, and the rest you get to keep for yourself. And when the French Revolution rolled around, they didn't like that very much. So during the Reign of Terror, he made a one-way trip to the guillotine. Lavoisier. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Okay. First of all, definite proportion says what? Every compound, no matter where it comes from, has the same ratio by mass of elements in it. Okay. But multiple proportions says that if you have 2 or more compounds that are made of the same elements, but they're different compounds, then if you hold one of them constant, the other will be ratioed by mass, whole numbers, 1 to 2, 1 to 3, whatever the case may be. So the first condition is both compounds have to have the same elements in them. Right? Can't be this one. Right? That one has no chlorine in it. That one's got oxygen and chlorine comparison. That won't do it. Hydrogen and oxygen, hydrogen and chlorine, that won't do it. Aha. Because this one's out too. NO and NO2. That one satisfies the condition. It has the same elements in both compounds, and they're ratioed 1 to 2. Let's see. 7. A sample of chemical X is found to contain 5 grams of oxygen 5 grams of oxygen, 10 grams of carbon. Okay. 20 grams of nitrogen. Yep. The law of definite proportions would predict that a 70-gram sample of chemical X would contain how many grams of carbon? All right, let's see, how many grams would this be? If this is how many grams are in this sample, then that total would be 35, wouldn't it? 35 grams total. But now we have a 70-gram sample. Okay. So what does that mean? The ratio's got to be the same in both samples. That means everybody has to be doubled, right? 35 to 70. So if it says how many grams of carbon, we would have to double the carbon. Right? Pick the best answer. It should be 20.0. It's only 20. Right. So the best answer is E. Does everybody see the logic there? Right. 9. Which of the following statements from Dalton's atomic theory is no longer true according to the modern atomic theory? So we're trying to discredit Dalton. Elements are made up of tiny particles called atoms. That's still true? Oh yeah. Atoms are not created or destroyed in chemical reactions. That's true. Yep. All atoms of a given element are identical. So, not since the discovery of isotopes. So C is wrong. D, atoms are indivisible in chemical reactions. That's true. That's another way of saying B. All of these statements are true according to the modern atomic theory. No, they're not. So we had to read all the way down to be sure. And once we found that C was the right answer, then D and E couldn't be right either. Test taking techniques. 11. The chemist credited for inventing a set of symbols for writing elements and a system for writing the formulas of compounds, and for discovering selenium, silicon, thorium. We didn't talk about this in class in any great detail, but I'm sure it's in your book. So who created the symbol system that we use today? I think I mentioned his name, but I may not have stayed on the topic very long. Berzelius. He was a Swedish chemist. And he discovered selenium, silicon, thorium, and he also proposed the system of symbols for our elements. And I'm glad he won because some of the others were really way out there. 12, Avogadro's hypothesis. What did Avogadro say? If you have two gases in two separate cylinders, it doesn't matter what the gases are. If the volume's the same, the temperatures are the same, the pressures are the same, what has to be the same? The number of particles has to be the same. The number of moles. So let's see if we find one that works for that. Each atom of oxygen is 16 times more massive. No. A given compound always contains exactly the same proportion of elements by mass. No, that's the law of definite proportions. When two elements form a series of compounds, the ratios of masses, no. I can see where that was going. That's the law of multiple proportions. D, at the same temperature and pressure, equal volumes of different gases contain equal numbers of particles. That's it. That's Avogadro's law, or his hypothesis. The first scientist to show that atoms emit any negative particles was, let's see, wasn't Kelvin. Let's see, wasn't Rutherford. or Dalton. It's either Thompson or, oh, it's a Thompson, but it's not that Thompson, it's this Thompson. J.J. Thompson. And what did he use? Cathode ray tube. 14. Many classic experiments have given us indirect evidence for the nature of the atom. Which of the experiments listed below did not give the results described? Let's see, the Rutherford experiment proved the Thomson plum pudding model of the atom to be essentially correct. Oh, I think we can stop. E says all of the above experiments gave the results described. Now, this one did not. So we can stop there. What Rutherford's experiment actually did was it drove a stake through the heart of the plum pudding model. So what came out of it was the nuclear atom. Most of the mass is in the nucleus of the atom, a very small part of the atom, and the rest of it is essentially empty space occupied by electrons. 15. The scientist whose alpha particle scattering experiment led him to conclude, well, okay, that was Rutherford. So 14 and 15 are a flip side of the same coin. I gotta figure a better way to do this. Okay. 16. Alpha particles beamed at thin metal foil make what? Okay, we're still talking about Rutherford's experiment. When you fire alpha particles at a thin foil, they can do several things. They can pass directly through without changing direction. Right? That was part of the experiment. They can be slightly deflected. By attraction to electrons. I guess that's possible. I would expect them more to be deflected by grazing contact with the nucleus. But the alpha particle is positive, right? It's essentially a helium nucleus with a 2+ charge. So it could be deflected by attraction to the electrons. Be reflected by direct contact with the nucleus. Well, that's 2. Reflected or deflected. It could bounce straight back. So the best answer to this one is E, all of the above. 17. Which of the following statements about atomic structure is false? An atom is mostly empty space. Yeah, I'll go with that. Almost all the mass of an atom is concentrated in the nucleus. Yeah. The protons and neutrons in the nucleus are very tightly packed. Yeah, they have to be. The number of protons and neutrons is always the same in the neutral atom. Protons and neutrons is always the same in the neutral atom. Then, the number of protons, yes. That defines the element. That's the atomic number. But the number of neutrons can vary. That defines isotopes. Now, what happens when you get all those, it says they're tightly packed. When you get positive charges tightly packed like that in the nucleus, you know, what keeps them from flying apart? That's the job of the neutrons. The number of neutrons in the nucleus stabilizes the positive charge repulsion of the protons. In fact, when the elements get bigger and bigger and bigger, you need more and more neutrons to stabilize them because the effect of the neutron is very short range. That's another topic. That's nuclear chemistry there. Or physics, actually. Okay. There we go. 20. Which of the following atomic symbols is incorrect? Okay. So let's see. Carbon, chlorine, phosphorus, potassium. Got your symbols memorized yet? Still working on them? Keep working, it'll come to you. So, is this right? Let's do the atomic numbers first. Carbon, Does it have a 6 atomic number? Check your chart. Yeah, that's it. Chlorine, 17. Yep. Potassium, phosphorus, excuse me, 15. That's right. Potassium has 19. That's right. Nitrogen has 7. Oop, there's the bad one. They say it has 8. No, it can't. What would be 8 protons? 8 or something like that. Oxygen. Okay. So the symbol doesn't match the number of. If you know the number of protons, you know the element. Or if you know the element symbol, you know the number of protons. Right, they're joined at the hip. All right, 21. The element rhenium. You didn't have to memorize this one, but you do have to find it on the periodic table. Exists as 2 stable isotopes and 18 unstable isotopes. Rhenium-185 has in its nucleus. Rhenium-185. That's where that goes. So if you look up rhenium, it's right over here. There. 75 protons. So how many neutrons does it have? That many? 110? So D's the answer. How many neutrons, this many protons? How did I get that value? Subtracted this from that. Because this is the total of protons and neutrons, the mass number. Okay. Yeah. 22. Which among the following represents a set of isotopes? So if you're going to have an isotope, and we're looking at each one of these as individual isotopes, that one, that one, that one, that one. There are 5 of them. Which ones are sets of isotopes? First of all, to be an isotope, you have to have the same number of protons. So the first one has 20 protons. So we could match 1 and 4 together, right? They have different neutrons, same protons. So 1 and 4 is a set. And 21 protons and 19 neutrons for 2 has its pair as 5. Those 2 match up because they have the same number of protons. 3 is left out in the cold. There's no isotope of 3, Roman numeral 3 in there at all. So it's 1, 4, and 2, 5. Right there. Yeah, just for a little bit while you're getting ready. 28. A species with 12 protons and 11 electrons. 12 protons, excuse me, 10 electrons. Okay. So what does that tell you immediately? You're dealing with an ion. It's not neutral. In fact, it has 2 positive charges because these 10 negatives only balance 10 of those. You got 2 extras. So we're going to have a 2 positive next to the symbol. So what's the symbol? Well, 12 protons means magnesium. Right? So magnesium 2+ is C. Okay. '29. The number of protons, neutrons, and electrons in this one. 19, potassium, 39, with a +1 charge. Right. We know there are 19 protons. How many electrons are there? Well, we've got 1 more proton than we need, 1 more positive charge than we need. So that means the electrons have to be 18, right? 18 electrons. we'll only neutralize 18 protons, and that gives us that extra charge. But how many neutrons do we have? Well, 19 from 39 is 20. Right, so we have 19 protons. So it could be this one, or this one. 20 neutrons, any one of those. And then 18 electrons right there. E is the answer. Okay. And then let's go down. There we go. 33. Which of the following is incorrectly paired? Okay. You need to know the symbol here, plus you need to know where it's located. Now, I didn't have you memorize tantalum or ruthenium. I think. There's ruthenium. And tantalum is, where is tantalum? Lost. Here it is, tantalum. Tantalum and ruthenium. So let's see, which one is incorrectly paired? Strontium. Strontium is an alkaline earth. Yeah, is that it? Yeah, alkaline earth. Tantalum is a transition metal. Yeah, that's right. You just found it. In the transitions, right? In here. F is a halogen. Fluorine is a halogen. Yeah, that's right. H is a noble gas. Nope. Hydrogen is not a noble gas. Hydrogen kind of stands by itself. We put it over the alkaline metals for balance. And because most often when we find hydrogen in compounds, if they're ionic, it's going to be a +1 charge anyway. And everything in this family is +1 charge in an ionic compound. So D is wrong. Ruthenium is a transition metal, so that's right. So D is the wrong one here. 34. How about 34? Here we go again. Match the name and the symbol. Phosphorus PR. No, phosphorus is just P. What is PR? Down here somewhere, I think. Here it is. I get it mixed up with this one. One of them is promethium and the other one is protactinium. But I don't even know. So A is wrong. I guess we can stop. The rest of them are right. Palladium is PD, platinum is PT, lead is PB, and potassium is K. 35. Another incorrectly paired. Copper is Cu, is that right? Cuprum, yep. Carbon is C, yep, that's right. Cobalt, CO, yep. Calcium, Ka. Cesium, nope. What is Ce? I didn't have you memorize that one. Cesium is Cs. Ce is cerium. And that one is, here it is. Right next to lanthanum, right? Because in that crack, this whole group goes in there. So the next one from lanthanum is cerium. It's a lanthanide. 35, 36. Did I do that one already? No, I didn't do that one already. 36. Which of the following is incorrectly paired? Antimony. SB. Stilbium. Silicon. Si. Yep. Silver. Ag. Argentum. Argon. Ar. Yep. Astatine. That's the wrong one. Astatine is At. As is what? Arsenic. without the old lace. 37. Wasn't that story about using arsenic to murder somebody? Arsenic old lace, I think so. All of the following are characteristics of metals except. See, metals, are they good conductors of heat? Oh, yeah. Malleable? Yep. The pure metals are very malleable. They can be bent and shaped. Ductile. Ductile is kind of a kissing cousin to malleable. Ductile means you can stretch it. So we can take a metal, pure metal, and stretch it into long, thin wires. Often lustrous. Yep, if you polish it, it is. What happens if it's very finely divided, small particles? It's black. Only when you clump them together in a large enough piece and polish them do they luster. Tend to gain electrons in chemical reactions. Nope. Metals lose electrons. So everybody over here has a tendency to lose electrons in chemical reactions. And non-metals tend to gain electrons. Now it's just a trend. It's not absolute. But that's why we say tend to. You have to cover our bets. Okay. 41. You're given a compound with the formula MCl2. And we can do that because there's no element on the chart that's M. M stands for metal. Okay. You're told that the metal ion has 26 electrons. Okay, 26 electrons. What's the identity of the metal? Okay, we have to assume that this is an ionic compound. Halogens have a -1 charge in compounds. All right, so that means the total here is a 2-. That means this one has to be a 2+ without one element. Right? So if it has 26 electrons and it's a 2+ charge, that means it has 2 extra positive charges, which means 28 protons. Now we can find the element. 28 is nickel. So this compound would be written nickel chloride. We named compounds. We named compounds, didn't we? Did we name compounds? Which of the following names is correct? Yeah, we did. So wait a minute, nickel. Nickel has the possibility of multiple charges, right? So if we were to actually write the name out, it would be nickel 2+ chloride. Right, type 2 compound. Type 1s, you don't have to put that in there because the metal is always the same charge. And where do they come from on the periodic table? First group, second group, 4 of the third group, boron, aluminum, gallium, indium. They're always +3. And then silver, zinc, and cadmium have fixed charges. And the rest of the metals are variable. So they would be type 2. Those guys that I just mentioned are type 1. Let's see. I got some naming compounds down here somewhere. How many oxygen atoms are there in one formula unit of Ca3PO42? How many oxygen atoms are there in that? Well, PO4 is a polyatomic ion. So that's why it's in parentheses. We need 2 of them. So 2 times 4 is 8, correct? So we have 8 oxygens in that compound. Okay, now we get to some names. How do we name this compound? Well, first of all, is it type 1 or type 2? Can't be a type 3 because it's a metal non-metal. So iron, where does iron come from? It's a transition metal that could have more than one charge. Oxygen is always 2-, so this one has to be a 2+. So we would say iron 2 oxide. 48. The correct name for Ca2 plus. Do we have to say what the charge is if we say calcium ion? No, calcium is an alkaline earth, and that group always has 2 plus charge. So all we have to do is say calcium ion. It's a metal, so it's going to be a positive ion, and it's an alkaline earth, so we don't have to say what the charge is. So calcium ion, C, is the correct answer. How about 53? The formula for sodium dihydrogen phosphate. So we know we're going to have sodium, and we don't have to say, oh, well, it doesn't have a charge there because we know it's a +1. Dihydrogen phosphate. That's a polyatomic ion. So what's the charge on it? But you look in your table that you will have access to on the exam, and you find dihydrogen phosphate is -1 charge. So that's it. Just this and that, they balance the charges. Okay, A is the answer. I better scroll that. Chopped off too much of it. 56. All of the following are in aqueous solution, which is incorrectly named. Okay, why did I need to say that they were in aqueous solution? Well, first of all, they all start with hydrogen. So that means they're acids. And we can't name them as acids unless they're in aqueous solution. If they're not in aqueous solution, we have to use the other naming conventions. So, which is incorrectly named? H2SO4. That has an oxygen in it, so you don't start it with hydro. So you look at this part of the molecule, sulfate, H's become X, sulfuric acid. That was correct. H2CO3. Right, similar case, oxygen, that's carbonate, 8 becomes X, carbonic acid. Okay, H3PO4. That's phosphate with an oxygen, so it's phosphoric acid. HCN, HCN. There's no hydrogen there. I mean, no oxygen there, excuse me. So we start with hydro. So we say hydro. Then we look to this part. That's a polyatomic ion, cyanide. Hydrocyanic. Oh, that's wrong. This is our answer. That's the wrong one. And HCl is hydrochloric acid. Okay. Naming acids tends to give students the most trouble because it's sort of archaic. The naming conventions were we tried to standardize them, but they were sort of grandfathered in from the Middle Ages. Which of the following names are correct? Okay. Okay, so let's say sulfide, S2 minus. All right. Sulfur is in the chalcogens, it's an oxygen group. Those are always 2 minus. So yeah, sulfide, sulfur, add the IDE on the end because it's a non-metal and it comes second. That means it has to be IDE on the end. Okay. Ammonium chloride. Is that correct? Ammonium is a polyatomic ion. And Cl, chlorine, changed to IDE. So ammonium chloride is correct. The polyatomic ions have fixed charge. Okay. And that's the only positive one in the group, ammonium. So you use the type 1 convention there. Just say ammonium, All right. Acetic acid. How about that? C2H3O2. This part of the molecule is acetate. There's an oxygen, so we say 8 becomes ic, acetic acid. Okay. Think vinegar. How about barium oxide? Is that correct? Let's see, where's barium? Barium's an alkaline earth. It's always a 2+ charge. So that's a type 1 compound. We say barium, and oxygen becomes oxide. That's correct. They're all correct. Okay, we're going to fill out a table for this one. So how do we do that? Let's see. That's good. So let's draw our table. Let's see, we need 1, 2, 3, 4, 5 rows. 1, 2, 3, 4, and 5. Okay, and then we need 1, 2, 3, 4, 5 columns. 1, 2, 3, 4, 5. This is going to be the symbol. This is going to be the number of protons. This is going to be neutrons and electrons and charge. Okay. The information that's given, this is given 206 eV. That's it for that one. This one is given, given, and given. And this one is given, given, given. Fill that out. This one is given, given, and given. Okay, let's use a different color to fill in the answer. Red. Got red. Okay, so for this one, what's the charge that symbol is given? 0. Right, there's no charge on that one. What's the number of protons? You need your periodic table. Look up lead, 82. If it's neutral, you have to have exactly the same number of electrons, don't you? How about the number of neutrons? I'll say subtract this one from that. 4. And 8 from that is 12, right? Okay, so we got the first one done. How about this one? The symbol is going to be 31. Gallium. Does it have a charge? Oh, yeah. Okay. How about the number of electrons? Well, gallium has 31 protons, and it has a 3 excess charge. So that means the electrons are going to be deficient by 3 charges, which would be 28. Okay, got that one done. This one, 52 protons. Look at your atomic number, and that's tellurium. Right? Let's see, does it have a charge? Well, it's got 52 protons with 54 electrons. It has 2 excess negatives. Right? So there we go. Got that one. Manganese. Manganese. Whenever I say that word, I hear Bill Murray's voice in the back of my head. Well, Caddyshack. I'm just looking at the manual and talking to Chevy Chase. It's manganese. That's a personal joke, I guess. Anyway, manganese is 25. So 25 protons. And it's got a 2+ charge. So that means it has 2 extra protons. 23 electrons. And there we go. Our table's filled. Now let's see how red erases. Ooh, it's good. And my doubts at first. Let's see, got that one. This is similar. I'm gonna let you do that one on your own. Use the same sort of reasoning. How about symbols? Can we get these symbols right? Let's do these. Silver is Ag. Calcium, Ca. Iodine. Copper. We did that one earlier, actually. Phosphorus. P. That's just simple memorization. The next one is naming compounds. FeSO4. Type 1, type 2, type 3. Type 2. Metal, non-metal. Metal polyatomic, which is treated like a non-metal. So the metal is potentially multiple charges. So you have to deduce what the charge is on the iron. What's the charge on sulfate? You have to look it up, I guess. It's a 2- charge. So iron, that single iron, has to balance that 2- with a 2+. That's where we get the Roman numeral 2. Iron has to be 2+. It's the only way to get a neutral compound. NaC2H3O2. C2H3O2 is a polyatomic ion. It's acetate with a -1 charge. And sodium is a +1 charge. It's a type 1 compound because of the metal. So it's sodium acetate. That's it. Potassium nitrite, NO3 is nitrite. It's a -1 charge. Potassium is a +1 charge. That's all you have to say. It's a type 1 compound. Type 1 compound for calcium and the polyatomic hydroxide. Hydroxide is a -1 charge. Calcium is a 2+ charge. All right, that's why we have parentheses around the hydroxide, because it's a polyatomic. So calcium hydroxide is all you have to say. It's unambiguous and not redundant. NiCO3, that's nickel. I check where nickel comes from. It could have more than 1 charge. And carbonate, which is a polyatomic ion with a 2- charge. Right, that comes off of the table, right? You've at least looked at the table, right? Let's see. There it is right there. Right. The left-hand side is sorted by alphabetically for the name, and the right-hand side is sorted alphabetically for the ion compound. So we know that carbonate is a 2- charge, and if there's only 1 nickel, it has to be a 2+ charge. So Roman numeral 2 as a type 2 compound tells us what the charge is. That way, if we're presented with this, we can write that without any mistakes. It can only be this. There's no other way. The nitrate ion, that kind of got chopped off. In fact, that's not right. Nitrate ion, that 3 got moved up there. Nitrate is NO3-. Aluminum oxide. Aluminum is always +3, oxygen is always -2. So how do we write that? Well, aluminum and oxygen. If this is a 2- and this is a 3+, the best way is to cross them. 3 and 2. 2 times 3+ is 6+. 3 times 2- is 6-. They balance. Okay. Ammonium, NH4+. That's a polyatomic ion. Perchloric acid. In this case, you need to know that chloric is derived from chlorate. And chlorate, actually, it's not derived from chlorate, it's derived from perchlorate. Chlorate is this way. Perchlorate is this way. So that we just tack a hydrogen on it, and it doesn't start with hydro because we have an oxygen. So perchloric acid is HCl4. Copper 2 bromide. We know that the charge on copper now is 2 plus, because it says so. And then bromine. Bromine is always -1 charge. So we need 2 of them. We got some more. Let me see. Let me make sure there's no mistakes here, and we'll just skip this one. That's right. This is dichromate. Most of the polyatomic ions have an oxygen in them. It's kind of a clue. Now, when hydrogen, this is interesting. When hydrogen is bound to a metal, it will have a negative charge, a -1 charge. When it's bound to a non-metal, it'll have a +1 charge. Okay, so we say hydrogen hydride as the non-metal position for hydrogen. That's why sodium hydride, there are lots of hydrides. Calcium hydride, you can even write aluminum hydride. As examples. Nitrous acid, that's right. Dinitrogen trioxide, that's a type 3 compound, right? 2 nonmetals. So we just say how many of them there are. There's no charge balancing in a type 3 because they're not charged. And 10,2 iodide. 10 comes from over here, right? It's not a transition metal, but these metals right in here, except for that, these guys right here, could have multiple charges. So that means you use type 2 convention. And if you need to know that, let's see, the periodic table, yeah, periodic table's got charges. So at least for the metals, you can believe the charges. For the non-metals, I mentioned this before, I think. For the non-metals, those what looks like charges, they're really oxidation states, and they're not necessarily charges. Okay, we'll talk about that later. But for the metals, those values that are in each one of those boxes for the metals, those are charges. They can also be oxidation states, but for the nonmetals, if you have more than one, say for chlorine, chlorine's got 5 of them, 5 different values. The first one is -1. And that's what it is in ionic compounds. All these guys are -1 in an ionic compound, combined with a metal. If they're combined with another nonmetal, then we need another way to approach it, and we haven't got there yet. Okay. More formulas. Thiosulfate. That is a polyatomic ion, and look it up. It's a -2, so we have 2 sodiums because it's each +1. And I will let you run these. Let me see if there are any squirrely ones in here. There's a type 3. There's a type 2, type 1 acid convention. And pay close attention to these polyatomics that have oxygen in them. Right? If you look at them really quick, you can mistake, say, sulfite for sulfate or nitrate for nitrite. So watch those really close. There's a nitrate, there's a phosphate. This is acetic acid. I learned acetic acid differently. It's in your book now as HC2H3O2, and that's not wrong. But I learned it this way. CH3COOH. This is written in like an organic chemist convention. When you have a C here with hydrogens in between, that C is bound to that C there, and the hydrogens are out here. Okay, and then these 2 O's are like this, double bond to that O, and then an O here and an H. That gives you a little more information about the structure. And this carboxylic acid says that this hydrogen right here is the same as that hydrogen. This is the one that dissociates and makes the acid. These guys are bound too tight, they don't dissociate. So in this way of writing it, those three hydrogens stay put. This is the only one that's released in solution. You gotta have something that releases hydrogen to make an acid in aqueous solution. We'll talk about that later. Let's see, did we get that in this? No, that's second semester. Acids and bases. Okay, let's see, what else, if anything? Definite proportions, we talked about that one already. I'm not going to hammer that one. Multiple proportions, we covered that already too. Which of these doesn't have a Latin name? Iron, ferrum, copper, cuprum, sodium, natrum, potassium, calcium, and titanium is Ti. So that's the one. It doesn't have a Latin derived name. Which one of these is not likely to form? Well, that's an alkali metal, that's true. This is an alkaline earth, that's true. Arsenic group is in with phosphorus, they're always 3- in ionic compounds. So it's a toss-up between titanium and carbon. So if you look at titanium in your periodic table, you see, what does it have possibly? Titanium, yeah, it's be +2, +3, or +4. That's good. Carbon, how about carbon? Well, carbon's a non-metal. So it's not as likely to form a 4+. It's kind of in the middle. So the best answer here is this one is not likely to form that ion. Doesn't mean it can't. Let's see. Trying to think. This one. Calcium carbide, I think it's 2 here. Calcium carbide is a chemical that miners used to use in their lights. Back when they had open flames in the mines. It's kind of scary. But they would put calcium carbide in the little cup here and then add water to it. And it would decompose and produce acetylene. And that's what they would light. Just light it. You have an acetylene flame there for quite a long time. But of course, if you run into methane pockets or build up coal dust, then you're in big trouble. So that's why they switched to electric lamps. But in that case, the carbon is -1. 2 minuses balances 2 pluses. All right, let's see. We ought to be close. I hope we are, because I haven't got much time before we run out. We're out of lab. Lab is 3:50. We have to be out by 3:50. So let's see how quick I can finish up. Which of the following atoms, isotopes, or ions contain 23 protein? You can do that one. How about this? Which of the following compounds is incorrectly named? You can do that one. That's it. Okay. Any questions, comments, complaints?